Welcome everyone. My name is Lionel Unterreiner, research engineer at Geomodelers. I'm here to present you our work on the cloud-native, standard-based geoscientific workflow architecture. Our goal is to improve geomodelers' collaboration. Geosciences are dealing with several types of data on a very broad timescale. The work I present today focuses on geomodeling. We are working on workflows involving business entities and activities of the Earth modeling domain. Seismic and well interpretations allows to obtain horizons and faults raw data. They are interpreted to build up structural frameworks and to operate reservoir characterizations. This information will then be used to build up reservoir grids or basin models to realize reservoir simulation and propose well planning drilling objectives. These business operations are involving multiple geoscientific experts in different teams operating on multiple use cases while sharing data. Working in this multipolar domain raises multiple challenges. Here are a list of those we want to fulfill. Sharing data, of course, gain in flexibility to implement a wide range of use case scenarios, give the ability to choose to automate scenarios, and finally preserve the ability to control the quality all along the life cycle of the management of a field. Our approach meets completely the OSDU forum goals. The contribution takes place on the computing part, not addressed today by OSDU. We intend to help to progressively replace monolithic applications by a combination of service-based applications. For the reservoir domain, we provide the only existing, for the time being, RESQML v2.2 Reservoir DDMS as an external data service. Our DDMS is connected to OSDU through HTTP REST and ETP. On top of these APIs, our stack is made up of three parts: a set of applications, as micro or services, an automation engine to orchestrate these services into workflows, and a UI that reflects these workflows. Together, their purpose is to provide an innovative cloud-native workflow automation platform. There were recent attempts to enhance the collaboration aspects. The Big Loop links multiple monolithic softwares. They promote a vendor-specific solution that can run applications in batch, and they left to the user the choice to exchange standardized data. A second work focuses on the tracking of changes of the RESQML exchange standard. And finally, a third one proposed an IT workflow built with cloud technologies. We share the cloud spirit with this work, but with two key differences. Their architecture does not rely on standard exchange formats, and they do not propose automation capabilities. Following this introduction, every part of our solution is based on recognized standards, so I will start by recalling them. Then I will describe our architecture, and just after I will illustrate it on a business use case. Finally, I will conclude this presentation and give some directions for future work. The first kind of standard we rely on is on the industry side. Our work today intends to cover the RESQML v2.2 geomodeling workflows and usage, which is a part of the whole landscape I described on the first slide. we promote also ETP v1.2 for the exchanges in and out of our architecture. This work is also done in the context defined by the OSDU Forum Consortium, which is embracing all activities from seismic acquisition, processing, up to production management. Our IT stack draws on open source technologies hosted mostly by the Cloud Native Computing Foundation. We indeed embraced the cloud native approach, containers, service-oriented architecture, standard APIs, and DevOps practices. To go a bit further, we pushed a serverless execution model into our architecture with Knative serving. We naturally turned to an event-driven architecture with Knative eventing and cloud events. It enables interoperable, heterogeneous services as well as easy auditing and failing management. We also want to enable business users to develop readily understandable graphical representations of business use cases while working with energy standards. We therefore use the BPMN standard toolbox to design and process the workflows. I will show you later how this standard is used in conjunction with OSDU and the cloud execution model to easily design reusable scenarios. The notion of activity from Energistics and OSDU allows us to blend together these three types of standards. An activity template abstracts an application, its inputs and its output types. It can eventually lead to an ontology to explicit the semantic of the RESQML models. An activity as an instance of a template models an actual application, its inputs and or its outputs values. The activity model is therefore at the center of our architecture. It parameterizes the application, computational tasks, and so on. It pilots the automation because the generated events are related to the type of the activity, and it allows exchanging data between the applications thanks to its standard industry nature. Let me now describe the components of our architecture. The first one is a Kubernetes-based platform. It can include a heterogeneous collection of applications as services. Knative is deploying and managing modern serverless workloads. It provides also universal subscription, delivery, and management of events in the system. It is important to notice that the services do not need to be serverless to work in this architecture. We designed ours like this because they do not need important workloads. The second component is a BPMN compatible workflow engine for orchestrating the events and thus the services. It contains a cloud events router component that translates the cloud events to the BPMN engine API calls. The first component is a message broker, like Apache Kafka, for managing the communication between the components on a per-channel basis. The fourth component is a public API with the backend logic for working with the system. It is in charge for transforming calls to the public API to messages handled by the message broker. And finally, the bottom layer consists in a data service API. In our case, it is a RESQML domain data management system. Now let me unfold the pathway of the events. We first put in the landscape background the workflow orchestrator in its own namespace, a service. It will exchange information with an external data management service, and the broker to link producers and consumers of events in the cluster. First step, a user launches a workflow with an HTTP request. Second step, the workflow launcher pushes the workflow start event to the broker. Third step, the cloud events router is triggered by the previous event. It will give orders to the BPMN engine to start the given workflow depending on the start event type. Fourth step, the service BPMN engine moves the workflow instance forward and pushes a start event related to a given service to the broker. Fifth step, the BPMN task, alias our actual service, gets triggered on this new event. It performs its task by reading and writing data. Then it sends a finishing event back to the broker. 6. The BPMN engine gets triggered again on this finishing event and moves the task forward. The last 3 steps will loop until the end of the workflow's instance. At the end of the workflow instance, step 7, the BPMN engine sends a workflow finished event to the broker. There are 3 interacting profiles with this architecture. The application provider has to provide a semantic description, the activity template, and the corresponding IT service. The workflow designer that uses a UI to chain tasks by linking activity templates. He has the knowledge of the domain. And the final user that uses an existing workflow and provides activity instances for each task. Let me now illustrate the elements of a very simple business use case, a fault surface generation workflow. There are 2 applications as containerized microservices, an MBA computation, and a quality measure. These applications are accompanied by 2 activity templates and as much activity instances as wanted. 2 are illustrated here with the actual parameters. A BPMN model was designed where each task has a list of ETP URIs as its input-output types, a header with the cloud event type that starts the task, and the cloud event type that finishes the task. And finally, the cloud events types that are used to start, finish each task, and the whole pipeline are created in the cluster. As an aside, the errors are also handled with cloud events. Here is the post request to launch the pipeline. The header of the request contains the cloud event specifics with the CE prefix. The data of the request contains the list of ETP URIs. This application, called Operate, allows us the monitoring of the platform. After a request, a token appears on the first task. A screenshot from the cluster shows a deployed pod called MBA. The first task ended and the token moves to the second task. Here the screenshot from the cluster shows a second just deployed pod. The second task ended and the token just moved to the workflow ended event. Without any workload, the pods will shut down. At the end of the workflow, you can use your favorite ETP client and watch the business objects and the triangulated surfaces, as shown here on the slides. I'd like to finish the presentation by emphasizing the main points. The management of geomodeling workflows is still challenging, but our solution, based on professional standards and IT standards, tackles several problems. Data sharing is possible thanks to RESQML ETP and OSDU. Loosely coupled services give more flexibility in scenario building. The activity model allows us to automate task execution and quality control evaluation. For the future work, we want to continue to explore other geomodeling use cases for reservoir grid modeling and geotechnics. We want also to propose this platform to other ESVs to cover more and more domains on a standard way, to finally converge towards a standardized Open Geoscientific Workflow Automation Platform. I thank you very much for your attention, and I would welcome any questions or comments via our website or email.